My name is Erdem. I'm the CTO at Chebiflow, and I'm going to talk about new kind of numerics where knowledge meets computation. And we are working on solving integral differential equations with high precision and full control of the accuracy. Today I'm going to talk about the work that we are doing at Chebiflow. That is, we are developing solvers for integral differential equations, ranging from just calculating definite integrals to CFD work, and also in finance or quantum mechanics, any type of differential equations. We named our talk as a new kind of numerics because we believe that it is time for change in how we are doing numerics. And I'm going to start with a classical Mathematica starting. If you are in an elementary representation of Mathematica, this is what you will generally see, pi to the 2,000 digits or 5,000 digits. And in here, I have two questions. Why at the beginning Mathematica choose to do this? Like why giving pi to the 2,000 digits? Why high precision calculations? And what we can do with this? That being said, let's go and see what we can do with this. So I have a model in here which requires a differentiation between 10 to the minus almost 200 and 0. And this is a snowwheel fluid modeling. This is an academic work done with Turkey in Boğaziçi University. And there we are modeling a snowwheel fluid, which is the fluid between your joints. I'm not going to go into detail of the model. This is your momentum balance. This is your concentration. And you have a viscosity parameter, which depends on the R value and the source term. This is highly nonlinear system. And depending on the R value, you are getting some flow profiles. And when R equal to some, like let's say 2.2, you're getting a flow profile like this. In here, the slope looks like 0, but it is actually not. It has to be really close to 0, but it cannot be 0. Then you almost lose the whole physical configuration of the problem. It is almost like the strain that you are going to apply to your knee will break your leg kind of problem. So the slope has to come to 0 to obtain physical solution, but cannot be 0. So in this problem, you really need to take advantage of what Mathematica is offering, that high precision calculation. But with that being said, how we are doing this? So we are looking into a steady solution in here and defining a parameter from this steady solution. When the du dt is equal to 0, this term is constant, and we are defining a k parameter, which has to be a constant parameter because it is equal to the derivative of it is equal to 0, and we define a special convergence criteria. It's not really that important for this purpose, like for this talk, but the k has to be constant. So with our method, with Chebiflow method, we are obtaining k constant for throughout the domain, and you see how many number of digits in here. And when you're using classical finite volume approach, this is what you get for k. That's supposed to be constant throughout the domain. And like in every numerical method, you have number of points that you're evaluating, you're discretizing your domain, and you are looking for a convergence, which is defined in here. With us, like the convergence exponential reaching to 10 to the minus 16 in this point, like around 200 around 100 points. This is log scale. And same for same R, this is the finite volume solver. And if just you extrapolate that slope, the slope of this curve, you'll reach somewhere here, which will be expected to be 10 to the power 8 points that you will need to obtain such a result, if it is possible without round of error propagation or divergence. This I kept doing it. I'm saving it. The rest will be larger. This is just the equations. I was never able to do that. So. That is messed up. Okay. Okay, I'll do that from here. Okay, much better. So when you have such a powerful numerical method, what we can do with this? And this is an example from Mathematica's documentation where we are trying to integrate this function. This is a highly oscillatory function. And when we were doing this numerically with our method, we found something peculiar, and we want to investigate a little further. And for that, we just drop this x in this integral, in this function, just for simplicity, and also that we can represent that sine square x as an exponential exactly. Just to show you that the sine x squared and sine x squared plus x is almost identical when you are reaching at the end of the domain. So they are really close functions. And as I said, we choose this way of doing this problem because we want to represent this function in two different ways. And I'm just going to show you that two functions are really identical. I'm not going to run this one, but what I'm doing in here, I'm getting an f1, f2. I am just symbolically subtracting them and then numerically doing the same thing. I'm getting symbolic difference equal to 0, and the numerical difference, whatever number of digits that I asked. So these two functions are numerically and symbolically identical. That means that when I'm integrating these two functions, I have to obtain a same integral result. So I'm going to integrate these functions symbolically. That's the important part. Then I'm going to evaluate them, and I'm going to just look at the difference with different number of digits. And what turned out to be the sine function gave as Fresnel, and this exponential function gave an error function. And I'm just first started with 40 number of digits. I get 10 to the minus 9, 45. I get 10 to the minus 9. As we go, 10 to the minus 9. So I'm not getting 0 in here. So there's something going on. So what we did is we numerically integrate using our method. First of all, sine x squared, and symbolically integrate that. And the difference between symbolic and our numerical calculation is 10 to the minus 9 as I keep increasing my accuracy parameter. That's what we call PV. And it is 10 to the minus 9. So there's something going on. So I went to the second function. Then I evaluate this function symbolically and keep evaluating this guy numerically. And I do get the result that I'm looking for, like 10 to the minus 50, 10 to the minus 500. So that means that what was happening in here is Mathematica was failing to evaluate the Fresnel correctly in that region. With that being said, so when you have such a powerful method, and when you are seeing such inconsistencies from time to time, the user has a question: how can you be sure that desired accuracy is provided? In that sense, we believe that we can be a numerical reference even evaluating symbolic functions with our powerful method. And we can do also other stuff with this. Of course, after seeing that, we had to do some our own Fresnel S, Fresnel C, and error function calculation. I'm just going to show you. These are really fast functions. These are, let's say, 30 digits. I just want to obtain them, and you get the 30 digits of Fresnel error function. And the next stuff that I'm going to show you are little solvers, let's say, per se, that checks if the given function, ND function, is C infinite. This is important when you are dealing with physical problems, such as heat diffusion, and you are putting diffusion coefficient, which is not C infinite. That means it is not something physical that you are trying to solve. The other one is the factorization, and we are looking into an ND function if it's characterized as a product or sum. This helps to increase the efficiency of your computation. Instead of, let's say, working a 3D array or matrix, you can work 3 1D arrays if it is possible to check this automatically. So let me run these ones. And also, as you see, for the first one, I'm giving a range for Z and for T to check if it is C infinite. And I'm going to check these almost similar functions if they are products or sum of the given ones. So yes, it is the given function in here is C infinite for the intervals given in here. And the function in here that I represented is not a product of T or X, but it is product of Z. That means that you can evaluate this part of the function, and you can evaluate this part of the function and multiply. That means instead of working with 3D matrix, you can work 1D and 2D. This will increase a lot the efficiency of your computation. And similar thing for the summation. You see, it is this time it is T that you can evaluate separately. This part you have to evaluate together. So again, 1D, 2D. That being said, let's look at the 1D integral where we find this Fresnel issue with us. And I'm just showing the method that is shown in the Mathematica documentation, and I'm hunting for a high precision result for 100, and I'm using the right symbolic definition to look at the exact result. And the times is 160 seconds for 85, 10 to the minus 85. For us, the time is for 42 seconds for almost 200, 10 to the minus 200. And I'm going to run a calculation for that just to show you. Let me just clean my kernel. Let me load my package. And I'm going to integrate this function. from 0 to 1 is a highly oscillatory function. And what I do only is I'm giving the function, I'm giving the limits of the integration, and how many number of digits I want to result to be given. And let me run this. And as Etienne was showing, I'm also able to show how many number of digits are converged throughout the calculation. So this is kind of nice, giving the user, hey, it is working, and also you see how many number of digits is converged in what time. And it takes 11 seconds, and you get a converged result. And if you want higher accuracy, you can just input a larger number in here. You can put 100. I'm not going to run that. It will do it. You don't need to change any method or anything. It will just converge. And things are, of course, more complicated when you come to the ND integrals. This is, again, an example from mathematical documentation. This is the function that we are trying to integrate. And what is given in here is, I just copy-paste from the documentation. Adaptive Monte Carlo with bisection dithering. It said that this is a satisfactory estimation. And I'm just going to run the same thing in here just to show what the result is. This is going to be really quick. It is like 0.3 seconds, but the convergence is 10 to the minus 3, let's say. What about, I'm working with Mathematica, I want high precision. Okay, so what about high precision? So I do the same thing with adaptive Monte Carlo, but this time I'm putting working precision for 100. So I'm shooting for something like 50 digits of accuracy. And I'm obtaining 10 to the minus 6 for 14 seconds. And I've been told that this is not the best way of doing it. So I just did use another method, which is obtaining a much better accuracy, actually, 10 to the minus almost 100 with 16 seconds. And what about us, what we can do? I am going to do something even harder than what I showed there, because that's really simple. I'm going to do 3D version of this function. So this is the 2D. OK, where's my mouse? This is the 2D function. This is the exact result. This is the 3D version of it. I'm just going to do the 3D version of it. Let's first start with 20 digits of accuracy. I'm just have ND number of digits 20. And let me run it. You have 20 digits of accuracy in 0.6 seconds. You ask for 200 digits of accuracy. You have it in 1.3 seconds. You have 200 digits of accuracy. And this is unlimited. You can do whatever you want. Like, you can just keep increasing. And in this M series that we like to call, we have this C infinite. And as you saw, this factorization. We have a solver for ill-conditioned linear system, eigenspace linear integer differential equation solvers. We have an ODE, which is the order of ODE is unlimited, where the coefficient for right now is the constant coefficient. But the order can be 100. I don't know who would use 100. Maybe the electrical circuits do need something like that, but we are capable of doing it. With that being said, I'm talking about accuracy, but accuracy is a really slippery word. I mean, it's hard to describe what you mean by accuracy. So I'm just going to give some facts about accuracy. So whatever you do as a digital representation or number of accurate digits, it is always limited, no matter what. It is not symbolic, so it is going to be always limited. And there will be always a round-off error propagation and amplification. It can be coming from your discretization method. And the resulting method will always lead to keep the largest error committed in the calculation. So, and also, it is really, really not easy to predict where this error is coming from. So the best is to use everything best possible, starting from your numerical calculation. That is our philosophy, that our results can confirm that we have the full control of the accuracy. That's important. I'm not always talking about high accuracy. I'm talking about giving the control of accuracy easily to the user. So we believe that we are able to do that with Mathematica and in using our method of doing numerical calculation. How we are doing this is, from the name, it is a little bit apparent to some people, I assume. It is, we are using theory of approximation from Chebyshev's work. And what we like to say is we are bringing 19th century math to do 21st century numerics. And we believe that it was first Fourier decomposition, then it came the theory of approximation. Now it is our time to do things. And why now? Why not like 10 years ago or when Mathematica started? This is really small. But what is you're seeing here, number of transistors on a CPU versus year. So when the numerical calculation started with finite methods, it was in here that those methods are designed for. So the computation power was really limited. We required the computation power. This is when Mathematica started, and it is still not there yet. But currently we are in here. We have 20 billion transistors in one CPU, and this is continuously going. So why to use a numerical method designed for this kind of computer? So there's a time for change in numerics. So what else we are doing? We are able to do little higher diffusion problems, let's say, coming to the computational fluid dynamics. And we like this kind of functions that multi-scale because they are not really easy to solve. And here, throughout my talk, I'm always having an analytical solution just to compare, as right now I'm going to have two. We have u of x in here, and then I know, so I can get the f of x. And I know the boundary condition. I'm just going to put a Dirichlet condition in here, a Neumann condition in here. That means that u equal to something, du dx equal to 0. So, and we are going to do first this steady version of it. And again, it's only going to be one parameter to solve the problem, PV. And again, I'm going to give the full control to the user, the accuracy. And I'm just going to compare the final result just to check it. And we have also an internal error estimation, which I'm not going to plot in here, but I can answer the questions later on. So for 1.2 seconds, let's say, you get 10 to the minus 6. Let's say I want 10 to the minus 50. And let me run that. It is going to be like 3 seconds or so. OK, well, 4 seconds, you get 10 to the minus 50. We can do similar thing with unsteady. OK. Sorry, let me first compare us with a simple finite volume solution. This one was the one that I first showed. This is the slope for finite volume. This is the slope for us. This is the finite volume solution. That is second order finite volume solution. This is us. As you see, this is lazier than this guy because we had that insulation boundary condition on the right-hand side, the Neumann condition. That makes it lazy to converge. And I tried to do this using ND-solve. And I use explicit Gunga-Kuttab. I don't know if this is the best way of doing it, but it took like 6 minutes to obtain 10 to the minus 20 result. For us, 10 to the minus 50 was 4 seconds. We can do this with an unsteady version and with our touch, Chebyshev touch, that during this calculation, I'm not going to ask anything about time step or a final time. The result that I'm going to give you is going to be continuous in time for you. OK. And let me just load my packages. Again, I'm choosing a function setup that I know the result, giving these two boundary conditions, these Neumann boundary conditions, both sides. And I'm going to solve this problem. OK, the calculation is finished. Now I'm going to ask you where you want to see the time. Let's say from 2 to 11. Or let's say 20 to 31. You have the whole spectrum of the time without any limitation of time step. And what about the accuracy? In here, let me just compare with the exact result. This is 10 to the minus 40 accuracy that we have. In this P-series toolboxes, we have this diffusion with different coordinate system, unsteady, again, different coordinate system, Dirichlet cavity, 2D and 3D, 2D Dirichlet cavity and 2D thermocouple cavity right now. And moving on to CFD, computational fluid dynamics, in the conventional methods, which I say like finite methods, at the end, the result that you are obtaining is a polynomial or discrete result is questionable. For us, it's for sure a continuous polynomial approximation. And this is really important because what you see in here, one polynomial solution. So meaning that whatever accuracy in here is the accuracy in here. So it's a global approach to the diffusion problem, which diffusion problem is global problem. And the important thing that you need to see in here, as the wall speed increases, you are stuck. There's a layer in here that is really small. And this is really hard to obtain with any finite methods because what they are not able to obtain a large scale and small scale at the same time. What they would like to do is put more points in here. As you put more points, the grids are not uniform anymore, and you just degrade your order of accuracy, which was already low. And on top of that, you cannot just be accurate in here. and saying that, OK, nothing is happening in here. The momentum transfer in here causes this flow to be stuck in here. So you need to be accurate everywhere. With this, we can do complex system. We are waiting on a patent in this. So we have a multi-material medium that I'm doing a heat conduction in here. I am applying a temperature difference in here and insulation. And this is a one domain problem for us. We are not really describing any boundaries for this disk, meaning that the solution is not jumping. Like we don't put anything like t equal to t, dt dx equal to dt dx. So there is no degrading of your solution. Solution is C infinite. Whatever order of your accuracy is, your solution is everywhere is the same. And we can do complex stuff like this, non-orthogonal geometries in heat conduction. And I'm just going to exit from the presentation because for some reason in the presentation I'm not able to show videos. And I'm just going to show you two videos to you that are we can do the similar thing with Unsteady. You have an analyst in here, highly conductive. The middle part is less conductive. So we can do this thing Unsteady. And for flow problem, I'm going to show you a Dirichlet cavity with a non-orthogonal geometry. In here, the important thing is happening is actually at the corner. This is really hard to obtain with any finite method. This is probably almost impossible to obtain such a nice result. That being said, we can also do flow problems. Okay, here. Flow problems with obstacles around it. And this is, again, the same methods that I showed you in heat conduction, and meaning that this solution is continuous. So the wall in here is part of the solution, actually, meaning that you are obtaining a C infinite solution, completely differentiable. And this will give you, let's say, an advantage while you are doing post-processing in CFD, which is really important when you are calculating stresses on the walls and things like that. To have a continuous solution is extremely important. And we are able to do this stuff in Mathematica, which generally in many of these talks, I never see Mathematica used in this manner. But Mathematica is a really clever tool. And if it is used cleverly, it can make a lot of things. And for our safety solvers, again, we are only talking about one parameter to control the accuracy. And you have all the accuracy that you want. You can be less accurate or extremely accurate. The user is choosing this. That's the important part, without changing any method, without any special things. And we are guaranteeing exponential convergence. It is guaranteed. And we respect the physics of the problem, meaning that if you have an experiment, and if you give me the exact boundary conditions from your experiment, you will see what you see in your experiment in your computer exactly. So that is really important, because we are not really using any ad hoc models such as turbulence, or we are not using any stabilizers to keep the solution stable. So it is respecting the physics of the problem. With that being said, we are working on right now an OD which this coefficient is non-constant, 3D versions of the solvers that I showed you. And also, we can also do many other things, like in mathematical finance, quantum mechanics, physics, biology. If you have an integral differential equation, it is our domain that we can solve it highly accurately. And with that, I just would like to thank you. And I'm happy to answer your questions.